So let's check it out. So it ends at 200, or 201, or 199, with a probability of 0.25, 0.5, and 0.25. And the previous 99 result may now in the second step move exactly for 1 meter, with a probability of 0.5, might also overshoot with probability of 0.25, or undershoot the probability of 0.25, and end up in 198 centimeters. And the same holds for the original move of 101 centimeters, may undershoot, be exact, or overshoot. So the correct answer is of course 5. I have now 5 possibilities. Now in order to get those probabilities, these are the probabilities of my first experiment. Whereas these probabilities here are the probabilities of my second experiment, given that I'm already in such a node, given the result of the first experiment. And so from Bayes' rule, you know that P of AB equals P of B under the condition of A times P of A. So we have just to multiply the probabilities. Going this entire blue path here gives us a probability of 1/4 times 1/4, which is 1 over 16. Going here, then there, gives us 1/4 times 1/2, which is 1/8. And going here, then there, gives us the same as here, which is 1 over 16. Now going first the green path here, we will have 1/2 times 1/4, which is 1/8. Going down here is 1/2 times 1/2, which is 1/4. Going down here is same as here. And finally for the right branch, we get the same as for the left branch, which is 1/16, 1/8, and 1/16. And now, since for example here, all those 3 possible paths will lead to the same driven distance of 2 meters, we have to add up those probabilities. And the same holds for the other values as well. So we end up with 1/16, 1/4, 3 over 8, 1/4, and 1/16. And what we applied here is the total probability. We were interested in the final outcome, P of B, which is the sum of B conditioned on A times the probability of A, summing up overall I. And so to answer our previous question, we now get a distribution like that. It's 1/16, then 4/16, then 6/16, 4/16, and 1/16. Now to visualize the same thing using distributions, we started with a distribution like that, which was the unit pulse, and then we convoluted it with a distribution like that, meaning we used that figure, multiplied it by 1.0, and put it here. And now in the second step, we did once more the same thing. We used that figure, but now for this value, since it's 0.5, we multiplied that figure by 0.5 and put it here. So this is 0.25. Then we multiplied the same figure by 0.25 and put it one to the left, meaning we put it here. And again, took it a third time, times 0.25 and put it here. And then we just summed that up. So that's 1/16. That is 2/16 plus 2/16 from the blue one, meaning 4/16. Now this is 4/16 plus 5/6, and so on. And so this is our final distribution. So in terms of programming, the only thing to do is you have one input distribution and a second distribution, and you convolute those 2 distributions by multiplying this distribution with one value of the other distribution and placing the result at the according position. Then doing the same for the next position and the next position and so on for all positions in this distribution. And it doesn't matter which one is which. And here's the code I want you to program. So here's the move function that you previously programmed, and here's the new convolve function that you should program this time. So it takes 2 distributions and it returns the convolution of those 2 distributions. And down here in the main program, our arena is still the same. We still move 3 times by a step of 20, but this time we start with a distribution that is just a unit pulse located at the position 10. Then again we plot it. Now down here in the loop, we don't just move the distribution, but we construct our move distribution, which is a triangle distribution with a half width of 2, located at M, meaning for a move of M, which is 20 in our case, I set up the move distribution not being centered on 0, but being centered on M. And then a convolution is done between the old position distribution and the move distribution, and the outcome is a new position distribution, and again we plot this. So now please implement the convolve function. And before you start, let me just show you how the result will look like. First of all, the robot is at position 10. It's a unit pulse here. Then it moves for the first time for 20. We get our triangular distribution. And then we move again. And our distribution gets wider. So instead of 3 values, we have 1, 2, 3, 4, 5. We move again and we have 1, 2, 3, 4, 5, 6, 7 values in our distribution. So this is the outcome you should expect.